Hello, thank you for attending my presentation, the remote sensing of large-scale subsurface habitability on Mars. As many of you know, there is a great deal of work concerning the interpretation of landscapes on Mars and what they tell us about the former habitability on the planet's surface. Today, we are going to examine how remote sensing can also give us information about the planet's subsurface. This image shows part of the rim of Gale crater, which is currently being explored by the MSL rover. What you see is that the rim is covered in dust and other aeolian deposits. And as you can see here, Mars today is an extremely dry and barren place. In contrast, this image shows you a fluvial landscape on Mars. What you see here are riverbeds that dissect the rim of a very old crater that was possibly also a paleo lake site. So from this type of images, we can tell that in its very early history, Mars had an active hydrosphere that included lakes, rivers, and very possibly a northern ocean as well. So here we see a comparison between some of these ancient river channels on Mars and some very similar channel systems on Earth in the Musa Bay in Iran. There are three geologic periods on Mars: the Noachian, the Hesperian, and the Amazonian. The Noachian, which lasted for about 300 million years, was very Earth-like, and it's a period when we have evidence of rivers and possibly a northern ocean. And then about 3.7 billion years ago, there's this really important episode in the Martian history because the planet changed completely. It went from being this very Earth-like planet to a cryogenic planet, basically extremely cold and dry. And these conditions have persisted since then. We don't really understand how the early Mars water systems during the Noachian were captured into the subsurface at the Noachian-Hesperian transition. But there's a popular model suggesting that the Noachian Northern Ocean underwent sublimation and it was cold trapped at the poles. And then basal melting of the polar cap materials introduced aquifers that then were sealed beneath an area of permafrost as the climate became colder and colder. Our understanding of life on Earth tells us that the biosphere and the hydrosphere have to be geographically coupled. And we now understand there is this general consensus that the hydrologic evolution of Mars is mostly a groundwater history. So there lies the importance to understand the nature of these subsurface potentially habitable environments. On Earth, subsurface water systems provide sheltered habitability. An example of this is Lake Vostok, which lies beneath about 2 kilometers of ice in Antarctica. And you can see that the lake is part of a very large systems of rivers and lakes. However, a major problem is that the exploration of these lake waters and sediments is extremely costly. Here we have a core sample of about 3.5 kilometers. Here's a view of the drill. So it's expensive to do this on Earth. So try to imagine, and like the engineering behind this is extremely complicated as well. So try to imagine doing this on Mars. It's kind of like very difficult, if not impossible at present. However, there is an alternative approach. This alternative is accessing cave interiors or their released interior sediments. One popular approach is to look for lava tubes. Lava tubes form when the lava flows solidify on top, but they continue to flow underneath the solidified crust. Here we see some skylights in a lava tube, And notice that the skylights, which are these holes in the roof, would allow us to access the cave interiors. So here's a possible Martian skylight, perhaps allowing access to an ancient lava tube. Here would be the skylight to the possible lava tube. This is about 35 meters across and about 20 meters deep. Now, consider this. There is no life within lava flows. It's impossible. It's basically molten rock. So to look for life within their interiors kind of implies that you would have to expect life to be delivered after the formation of the tube, or that life spontaneously arose within the tube after its formation as well. I believe that a far more attractive setting is something like this in this view. This is a subglacial cave with a meltwater origin. So here we have a cave, we have the shelter, and we have the presence of water as well, liquid water, both very good ingredients for like the preservation of habitability on Mars. A problem is that we don't know of any of this type of caves currently forming on Mars, and their stability is likely very short-lasted. Now, there is a completely different type of cave on Mars that I'm sure you've never heard about. And it's actually connected to the chaotic terrains and the outflow channels. So let's talk about these now. So first, a little introduction to the outflow channels and the chaotic terrains. So this is a picture that was taken about 50 years ago by the Mariner 9 spacecraft. And so here we have a chaotic terrain. Okay, so a chaotic terrain is basically, this is about 300 kilometers across, as you can see. And these are broken up crustal fragments. Okay, so the chaotic terrains on Mars connect to these huge channels. Again, look at the scale here. So this here could be 20 kilometers or so. And so these are some of the largest outflow channels, some of the largest channels in the solar system, if not the largest. Here we have a much nicer view of these chaotic terrains and outflow channels. And this is exactly the same area that I just showed you, these 300 kilometers here. And this is a digital elevation model, by the way, that was obtained using MOLA topography, the Mars Orbiter Laser Altimeter, for the 1996 Mars Global Surveyor. So what you can see in the topography here is that there's large scale collapse, the chaotic terrains that I mentioned before, and the crust is all broken up into these knobs and mesas, and like all these chaotic terrains connect to vast outflow channel systems. Okay, the relief here right here is about 2 kilometers, and here's about 500 meters. So there is like a range of relief in chaotic terrain formation. Yeah, but the main thing to see here is that there's like really widespread crustal collapse that is connected to surface flow erosion over these immense scales. And the interpretation of this is basically that the chaotic terrains are formed when an aquifer outbursts. The aquifer collapses, it releases a lot of water, and the water flows on the surface and produces a catastrophic flood. So this comes first, this comes second. The water comes out from the subsurface, like it reaches the surface and it flows and it produces huge floods. So, but here's the thing. Do chaotic terrains really represent paleo-aquifer locations? Here's the Shalvatana case. So this here is Orson Welles crater, which is the head of the Shalvatana channel, this outflow channel here. Look at the scale here, it's about 500 kilometers here. So again, these are immense features on the surface of Mars. And like, this is actually a very important question, okay? So, because it kind of like goes back to this preconceived view connecting chaotic terrain to aquifers and the source of the outflow channels that has been there in the literature for many years, for like 40 years or so. Shalvatana is really important. an Orson Welles crater. Okay, so why is it important? Because basically, the Orson Welles crater is not a chaotic terrain. Yes, it's like somewhat modified by collapse, but it is not a chaotic terrain. It is an impact crater. So basically, you have an asteroid hits the surface, it produces a huge hole and ejecta that flows away from the crater, and then you end up with like something like this. You can even see the ejecta here, all these rays and ridges, right? So this is the ejecta blanket. So wait a minute. So then, if this is not a chaotic terrain, then where is that channel coming from? Where is this channel coming from? So let's take a look at um, the regional setting here, and I'm gonna talk about like evidence of giant conduits here. So here again is the Shalvatana outflow channel and the source crater. This here is about 110 kilometers, 400 kilometers scale here. So what you see here is that the Shalvatana source crater is connected to this area of surface deformation, and this linear zone of deformation extends into this huge chasma or canyon. This is actually about 6 kilometers deep, and these interior materials are thought to be lake deposits by some people. So, so if we have like paleolakes here and here, the idea is that the water drained through the subsurface, it reached the crater and then overflowed to form the channel. Now, so if the water is flowing through the subsurface, is possibly producing or flowing through a pre-existing conduit, because that's the only way you can sustain flow rates capable of producing these catastrophic floods. And when we look at a close-up view of that channel, that area of warping connecting to the source of Chalvatana, this is what we see. See evidence of surface warping, like for example here, and here you can see the relief is about 2 kilometers. And here we have like some tilted blocks. Well, the idea is that we have basically a conduit here, like a very large one. This is 30 kilometers that collapsed, and like the ceiling of the conduit warped and locally collapsed to produce this immense feature. So now we're looking at what could be possibly the roof areas of some of the largest caves in the solar system. Of course, you're going to ask yourself, how is it even possible to have a cave system of this dimension, right? Like, as I said, this is like 30 kilometers, and I'll show you more about like the scales of these features in a minute. Well, the answer is that we don't really know. Like I'm actually like doing some research on this now, and one possibility is that these are nested conduits as opposed to single ones. That's something that is still unresolved. So here we have a close-up view of part of that area of subsidence that I just show you, and I just want to show you this for scale. So this area of subsidence here is like 20 kilometers, and this is the San Francisco Bay Area at a similar scale. So basically, you could fit most of San Francisco inside this hall here. And now here you can see like the red areas are zones where a few years ago I mapped the distribution of these conduits, and by comparison, these are the same scale. You can see the size of the UK here. So these conduits are not just large in their width and length, but also in their scale of integration. So we are looking at a history here of vast subsurface river erosion, delivering huge amounts of water to the outflow channels. And so it would be really nice to be able to explore these caves, right? Now here, I just want to show you again like the dimensions of these conduit systems, right? But what we have here, I took out all the conduits, and what you see in yellow is only the areas that are affected by subsidence, including the conduits. And of course, this is not Mars, this is a map of Europe. But you can see that this area of subsidence, let's assume that is undermined by these conduits, is like a big chunk of Europe, right? So we're looking at huge, enormous features on the surface of Mars that are essentially unexplored. So we want to explore these outflow channel giant conduits, right? The, it, it's very difficult. It's extremely difficult. It's first of all, it's unclear whether the conduits have experienced complete collapse or closure, and whether they still retain significant cavernous space. And this is developing research as well. I would say that like preliminary results indicate that, yeah, there is still some like conduit space that remains in the subsurface. However, accessing these subsurface structures is going to be, it would be an incredibly difficult feat because they are deep, like they are very deep, and like maybe um, like a couple of kilometers deep. So, so here is an alternative. What if we focus on the materials that were expelled from their interiors during the release of fluid phases? Okay, so there are two major areas of interest connected to the release of these materials. Like one is marine deposits that formed within the Northern Ocean and marine deposits that formed within an equatorial sea basin. So I'm going to talk a little bit about this. So first of all, let's talk about the Northern Ocean connected to the release of these outflow channels. This is really well established through very extensive literature, and the hypothesis is essentially that here we have the outflow channels and the northern plains. So the hypothesis is that about 3.4 billion years ago, um, like the water released from the subsurface reached like the northern plains basin and it formed an ocean. On Earth, there's nothing like this. I mean, we have like groundwater fed lakes, but the marine scale is unprecedented in our geologic record. So the ocean of Mars, the Northern Ocean, was vast. It could have occupied as much as about a third of the planet's surface, but that's still not really well understood. So this slide here is basically a problem. So what we see here, like the northern plains of Mars, is pretty much the extent of the Paleo-Oceanic basin, right? So you would expect that you could just land anywhere here and sample the marine deposits and then sort of like make a guess to what kind of materials came out from the subsurface here. Well, that's not the case because from here to about here, basically almost the entire northern plains basins are covered by very extensive latitude-dependent mantles, which are basically water ice that condensed during the sublimation of the polar caps that happened or happens periodically when the planet tilts towards the sun during a high obliquity. So here we have a view of these mid-latitude mantles. Very exciting in a way. You have all these polygons that look very much like Earth permafrost, and this impact seems to be exposed in some ice. But basically atmospheric emplaced excess ice and pretty young. So not the Northern Ocean marine sediment record that we would like to see for this particular research project. So essentially, landing on the northern plains would entail a significant risk of touching down on young mantles that are not connected to the paleo marine environments sourced from the outflow channels. However, the recent discovery of possible megatsunami deposits offers another potential research window because they are marine landforms that remain at the surface with apparent little resurfacing. So these illustrations like show you basically like a normal wave. It has an amplitude of a few meters generally. And then, so this is the surf zone. You can basically, when you go to the beach, you'll see that the wave comes and then goes without much like run up. This is a tsunami. It's a totally different thing. Like you can see the amplitude here. The amplitude can be huge and they can move extremely fast. So the run-up elevations are significantly far and above the normal sea level, which is good news for us, right? Here's an example of these run-up mega tsunami deposits inland, and these are some mega tsunami deposits that are against like some cliff walls. So these are a lot of these materials are marine materials that were transported by the wave. And a history of 2 mega tsunamis on Mars. Okay, so so this research shows a reconstruction of the ocean 3.4 billion years ago, and it indicates that there were 2 paleoshorelines, one at minus 3,800 meters and the other one at minus 4,100 meters, and there was a recession between the two. Okay, you can see that it goes from high up here to low down here. Now, this high shoreline was the source of a major mega tsunami deposit that I indicate here, and the lower shoreline, the source of another major mega tsunami deposit. What is interesting about this is that we can sample these materials, okay, because they are at higher latitudes and they retain a lot of the primary emplacement morphology. So we know that they are not covered or modified. So this is an access window to the ocean water that, as I mentioned, probably came from the subsurface. So let us talk about the geomorphology of the older megatsunami deposits. So here's a view of the older megatsunami deposit. You can see that it has a lobate front that goes around pre-existing topography. Notice that this is the up direction here. This arrow here indicates the location of a promontory. So basically a topographic high. And the idea is that as the wave propagated up, it went around the promontory and then it deposited this sedimentary load. The sedimentary load is very boulder rich, as you can see here. This is 100 meters, and even at this resolution you can see individual boulders. So it tells you that the flow had to be extremely energetic as it propagated up. Another very exciting characteristic of this mega tsunami deposit, this older mega tsunami deposit, is the presence of backwash channels, as we see here. So this is this map shows their distribution. This is 100 kilometers here, and like the areas in green basically indicate the locations of this type of channeled surfaces. Like this particular one is a close-up view of this area here. What is interesting here is that these channels start abruptly along a constant elevation here, right? And so the interpretation is that essentially the wave, the mega tsunami, came all the way up here, or like somewhere up to here, and then it, you know, it's gravitational, it's unstable, so the water washes back into the ocean this way, and as it washes back, it flows over all these surfaces and it dissects them, producing these huge, enormous channels. Okay, this is 4 kilometers here. So this image is a close-up view of one of those backwash areas, and you can see that this is one of those channels. Okay, and you can see the dissection by the channels has produced these streamlined bars that are composed of very large boulders. Like these are about like 10 meters in diameter. So these are huge features, again indicating that there was a very energetic event, like a very energetic flow event that produced these channels. So this view here is not Mars, as you can see, there are houses here. So this is Indonesia. And like what happened here is that there was a tsunami, and as the water washed back into the ocean, So it produces these backwash channels as well. And what is interesting here that I haven't mentioned yet is that this is the coastline, right? And so as the water that is like carrying a lot of sediments goes back into the ocean, it deposits sedimentary logs close to the ocean. You can see some of these materials possibly being deposited in this area. And you see something very similar on Mars. You see these interpreted backwash channels, and this is the predicted shoreline from the mapping that we did in 2016. And so the water washes back into the ocean, and when it reaches the shoreline, it produces a sedimentary lob. This is really interesting because if this hypothesis is correct, and then landing here could give you access to marine deposits that are still present at the Martian surface. So let us now take a look at the geomorphology of the younger megatsunami deposits. So here's a view of one of those younger megatsunami deposit fronts. You can see that it shows no evidence of backwash. So basically the flows propagated, and when they stopped moving, that was the time when they become stable at the surface, mechanically stable, and they don't flow back. That could be because they froze in situ during their propagation, or it could also be because of a very muddy composition. We don't really understand why exactly yet. I think it's very likely that it represents an in situ freezing process, and that would actually indicate that this megatsunami formed under much colder conditions than the older one. In fact, there is evidence for a significant time gap between the two proposed megatsunami events. The evidence includes the following. So here you have an area, a ramp, that is dissected by the backwash channels associated with the older megatsunami deposits, like the backwash phase of that megatsunami deposit, right? Now, you can see that the front of these materials consists of a scarp, and that there's a shallow trough that cuts into these channeled surfaces, right? So you can see it here, you can trace it this way. And then this shallow trough was intruded by one of these younger megatsunami flows. And this indicates that in between these two events, there was a time interval lasting sufficiently to allow for large-scale surface erosion on the formation of these canyons. So that could be like hundreds of thousands of years, maybe even longer perhaps, and it indicates it would be consistent with the phase of glaciation in between the two megatsunami deposits. So again, this tells us that they happen at different times, like the older megatsunami deposit and the younger megatsunami deposit were separated by a significant amount of time and probably occurred under different climatic conditions. So one of the reasons that we were talking about these megatsunami deposits is because we are interested in understanding the nature of the aquifers that released the water that formed the Northern Ocean, right? The late Hesperian Northern Ocean. So let's think about this for a little bit, okay? So we know that, so you have these outflow channels discharging these massive catastrophic floods. They fill the northern plains with an ocean. But if this ponded water was there for a very long time, it possibly changed composition, and this changing composition could be reflected in the materials contained with these two megatsunami deposits. So as a consequence, sampling these different megatsunami deposits, these two source of materials, could give us information of how the habitability of the ocean evolved with time. The other interesting location is this inland sea that also was sourced from the outflow channels. And in this case, it's equatorial and tropical. The equator runs right this way. So there is no IEC mantles that we have to worry about. So let's look at this study. So when you see here, this white line here is basically a near, like a constant elevation line, okay, at minus 3,800 meters. So this forms basically the boundary of an enclosed basin. And notice that this basin is located at the convergence of like many of the outflow channels of South Sea, right? So all these outflow channels, when they discharge water, the water went right into this basin. An enclosed basin and water pond, like flowing into the basin means ponding, essentially, right? So all these black materials are very interesting. These black markings are very interesting because they represent the locations of sedimentary mantles that are bounded by this elevation, and I'll show some examples of this. And this topographic control, like this topographic demarcation below this elevation, implies that they most likely formed during marine sedimentation. So here we have some of these materials. You can see this line here is that basin margin, and here is the basin margin as well. And you can see that the mantles don't really extend beyond the line. Here you have like some outflow channel bed forms, and you can see this very clear correlation. And here's this area here is right here. So here we see the mantles, right? So they are very smooth and they show no evidence of flow induced modifications. So possibly because they actually settled by vertical precipitation within the marine body, right? So this would be a very interesting area to explore, to understand the nature of these aquifer released material. So here we have a numerical simulation that indicates basically the time that this inland sea takes to disappear. This is the initial ponding with depth, and you can see that after 1,000 years, this is all that remains, Hadriatic scales. What is interesting about this is because of the really rapid dissipation in geologic timescales. 1,000 years is nothing. The groundwater composition released from the outflow channels could be relatively well preserved in this area. So Hadriatic scales is really interesting, from these and other perspectives. So here we have a view of Hadriatic scales. Okay, and as I mentioned, this chaotic terrain would have been a lake residue from the inland sea. Okay, let's see what the geomorphology tells us about this. So the floor of Hadriatic scales has these mesas that are flanked by these terraces, and you can see them here, and they are very similar to wave cut platforms. This is the area of cliff recession at the waves come and go and the cliff retreats. So you can see these huge possible wave cut platforms. So basically the geomorphology, even at this scale, is telling us that water could have ponded in this area. So here's a really interesting implication of this study. What if the Mars Pathfinder actually landed on some of these materials in 1997? So here we have a very interesting paleogeographic reconstruction. Here we have the Pathfinder landing site. Here we have the inland sea and the Northern Ocean. So you can see that the landing site is right in between the two of them. So you could characterize this outflow channel floor as a spillway area. And the materials that we see at the landing site might be marine sediments that were released during the flooding of the inland sea. So this concept is actually well predicted by this numerical simulation. For example, here we have the velocity, and this is the area of the inland sea. that is ponded, then when you actually flood it from valles marineris, you produce waves that propagate through the inland sea, and they discharge along its margins, reaching the pathfinder site. Thank you very much for attending this presentation, and I leave you here with a brief summary.